Hello, Giovanni here at Frap Tools, and this is BAGAI's tutorial. Today we're gonna take all the time that we need to explore its features and perhaps compare it with its sibling Sapel. BAGAI is one of the most protean modules that we have ever made. It can do so many things, so there might be a lot to unpack. So let's start with the interface. As it is always the case with our modules, you can use the colors to understand where you are on the interface. It consists of 6 sections, each with its own color. We have a clock in yellow, so every yellow element on the interface will belong to the clock. And then we have an analog thermal noise generator with a filtered output, which is in gray. We have a sample and hold circuit, which is in orange, and its 8-bit quantized version in red. Then we have a fluctuating random voltage generator in white, and finally a clock burst generator in green. So let us start with the simple clock output, which is this one. The clock has the same feeling of Sapel's one, and perhaps it has a slightly extended range. It features the mandatory plus and minus randomized versions, so the plus clock will output more clock than the regular one according to the global rate of change, as in Sapel. More on this in a minute. And this one will output less clocks than the regular one, while still the main circuit is having a regular beat. Those two behaviors reflect the more than and the less than mode on Sapel, but they are available at the same time, so we can use them in different points of our patch. So for example, I can use the less than mode to clock envelope every now and then, and I will use this envelope to control the FM amount. And I can use those random bursts to control another filter that I can monitor here. Sapel had clock modulation input on unattenuated. Here we have a CV input with attenuverter. So if we set this Falistri to LFO mode, we can use this LFO to modulate the clock speed. And if we use a bipolar signal, we can also slow it down. Of course, we can use, if we want, an external clock to trigger BAGAI by patching it to the clock input. Now this knob won't have any effect, and BAGAI will generate clocks, both regular and random, based on this other clock. And if you are familiar with Sapel, you will know that this button here will freeze the sample and hold and the clock outputs. On BAGAI, we also have a button that might have some differences that we will see in a minute, but for now, the behavior is the same. Just like with Sapel, we can use an external gate to play the clock and stop it. So for example, we can use the end of rise and end of fall gates from this file history to control the playback of our random generator. So we'll see that we are now able to stop the clock with an external gate, as shown also by this LED here. Just like on Sapel, BAGAI features a thermal noise generator, but instead of having 4 noise outputs with different noise colors, we have a single output with a variable color. So we can emphasize the low end or the high end, which plays always good on a filter. The third section we want to explore is the orange one, the sample and hold circuit, which is much like Sapel's sample and hold. It has some differences. So the first one is that this control is bipolar. So if we patch it to the brainsaw, we can see that the frequency is going also down instead of going up only. Compare this to this. The second difference is that this sample and hold has an input, whereas Sapel's one only sampled its own thermal noise. The default sampling source of this sample and hold circuit is the unfiltered white noise, which gives us this stepped random voltage behavior. However, we can sample other sources, preferably bipolar ones. So for example, we will use this LFO that we just used. The result is a stepped series of values that goes up and down according to the LFO frequency. And you can also appreciate how low this sample and hold goes, because it covers the full 10-volt range. So if we patch it to brainsaw's volt per octave, we will have a scale spanning on over 10 octaves, which is a bit undesirable. So if our goal is to have this kind of behavior, we can just attenuate it with the exponential FM circuit. Now that everything is in a more controlled pace, we can see the difference in terms of range. Another difference is that Sapel's sample and hold circuit freezed when we pressed the button, and the clock stopped at the same time. Whereas on BAGAI, if we push the button that holds the clock, we are able to stop the clock, but the sample and hold continues. So this button only affects the output. The reason is that with that setting we can achieve slightly more complex patchings. For example, this. So by using the end of raise gate signal from the LFO that we are sampling, we can sometimes stop the clocks from modulating the wave folder, while the sample and hold keeps sampling and holding. Of course, if we want, we can use an external clock to trigger the sample and hold without affecting the yellow clock. If we want to replicate the same exact behavior of Sapel's button and gate on BAGAI, we can simply cross-patch the main clock output back into the sample and hold clock input. The red section offers the same sampled signal, but quantized in an 8-bit grid. So when this knob is all the way to the left, the sound is gonna be the same, because it will still output unquantized sample and hold voltages. However, as we increase it, we are reducing the bit depth. So we are reducing the number of possible values, starting from 256 all the way down to 2. And now comes a crucial feature of BAGAI, because this clock and this input can work at audio rate. So let's patch this output straight into the mixer and set this switch to the upper position. Now we are using an exact parallel clock, the yellow one. So while the yellow output are still outputting low frequency clocks, this switch switches from this behavior to a much faster one that can go up to 30 kilohertz. So now we are listening to the noise sampled by the sample and hold circuit, which means that if we use another signal, for example a sine wave, and patch it to the sample and hold input to override the thermal noise, we are able to sample it with an analog sampling process. Which also means that we can now use this section as a downsampler. So if we use our LFO to modulate the clock speed, we can now modulate the sampling frequency, the sample rate. Things can become even more interesting when we use the quantized output, because this can now become a bitcrusher. Until we are left with a squared waveform. A cool trick that I like to use is to set both oscillators to respond to the same volt per octave signal, and use another oscillator square wave to clock the sample and hold circuit, so patch it here. This will remove this clock here and will establish a connection between the sample rate and the oscillator's frequency, making it more consonant. And we still have this output here that we can use perhaps to clock our sequence. And we will thus have a patch where the same knob controls both the sample rate and the sequencer speed. Let us approach the white section, which is a fluctuating random voltage generator, much like Sapel's one. Also in this case we are dealing with a bipolar control with a wider range, so -5 to +5 volts. So if we take the bitcrusher output and patch it to the Kunze filter, we can use the fluctuating random voltage to control the cutoff frequency. As you can hear, it can go very fast, as opposed to Sapel's one, and has a much wider range, also bipolar. However, as we rotated this knob here, the random clocks that were triggering Brainstorm's wavefolder almost disappear. And the reason is that, just like in Sapel, this knob defines also the global rate of change, which is how likely the random clock diverges from the main one. You can see that as I rotated, my triggers on the Brainstorm will appear again. This control is also influenced by the probability distribution which defines the probability of different voltages than the median ones to appear, much like in Sapel, and both the probability distribution and the fluctuating random voltage speed can be voltage controlled. So let us use the fluctuating random voltage to modulate the frequency of the first two filters through Kunsa's volt proactive input. You can hear that as I increase the probability distribution, the filter will tend to stay very open. And as I reduce it, they will stay more closed. We can use an external CV to modulate both the fluctuating random voltages, clock speed, and the probability distribution. For example, in this patch we're gonna use an LFO to modulate the clock, and perhaps we can cross-patch a stepped random voltage to the probability distribution to randomize the magnitude of our fluctuating random voltages. We must keep in mind, though, that the control voltage over the clock passes through an attenuverter, while the one over the probability distribution is directly summed to it. The final section that we are going to explain today is the burst section. As the name suggests, it generates clock bursts that come out of this output here. And it does so by combining two separate clocks. One, which is the yellow clock, and the other one, which is another generator modulated by the fluctuating random voltage output. Check out the difference among the three clocks. This is the regular one, this is the more than mode, and this is the burst. The burst behavior is heavily influenced by the position of the global rate of change and its probability distribution. With extreme settings, we may experience only the main clock. And with other extreme settings, we may experience too much burst. We can use the burst gate input to stop it. And so we use a gate on the first two stages of the sequence to play the burst and the gate off to stop it. Of course, we can use the clock burst section with other clocks. So I can take, for example, this random output and patch it here. And to wrap everything up, I would like to use a very simple technique that my friend and colleague Federico used at Superboot. So I'm gonna take the clock output and use it to ping a resonant Kunsa, use the bandpass filter output to have this very rumbling kick drum, which I will then patch to the sample and hold input, use the bitcrusher output, and now I have a kick drum whose sample rate depends on how fast it goes. And now I can bitcrush it. Some very extreme tones to wrap this in-depth tutorial up. Today we covered the basics of this module, and in the next episodes we will see how to put it into creative patches and practical applications. If you have any questions or any suggestions, let me know in the comments below. I hope you found this tutorial useful, and I will see you next time.